Resistors in series and parallel. So this circuit looks very similar to the circuit for the capacitor problem we did earlier. It's basically the exact same setup, and we're going to go through it in the same way. This time, because we're not dealing with capacitors, we're dealing with resistors. We're looking for current through each resistor and potential difference across each resistor. So we're going to start at the end, and basically these problems in physics, like most problems, you get a little overwhelmed at first. There's a lot going on. Just pick some little part of it that you can do and take a bite out of the problem, and then step back and look for another little part. So I see here right away I've got 3 resistors. I'm going to mark them here in how about a yellow highlighter. I've got 3 resistors in series. So the first thing I'm going to do is deal with those 3 resistors on that yellow path that are in series. So I'm going to redraw this circuit. A, B, R1, R2, R3, and those 3 resistors I'm going to turn into one equivalent resistor. I'm going to call that R equivalent prime. And so this is a series operation, and in series we add the resistances. And they're each 4, so 4 plus 4 plus 4, 12 ohms. So I know my equivalent resistor for those 3. Now, I guess I should write it in here somewhere. R equivalent equals 12 ohms. There we go. Now I have 2 resistors in parallel. Again, I'm just sort of taking bites off here. As I come into this junction, there's 2 parallel paths. One comes this way and one comes that way. So R2 and R equivalent prime are in parallel with each other. And so I can redraw this circuit. R1, R2, and I can combine those 2 resistors that are in parallel into one equivalent resistor. I'll call that R equivalent double prime, and those are in parallel. So when you have resistors in series, you always end up with a bigger resistance for your equivalent resistor than any of the individual resistors in series. And when you have resistors in parallel, you always end up with a smaller resistance than any of the individual resistors, because it reduces the overall resistance by adding those extra paths that the electrons can take going from one side to the other. And what do I get? 1 over 4 plus 1 over 12. That's 12 over 4. Oops, no. There we go. That's better. And don't forget to invert it at the end. This is 1 over, I'm just going to write it here, 1 over R equivalent. And so we have to invert that at the end. We get 12 over 4, which is 3 ohms. So this is equal to 3 ohms. And now what do I have? I have 3 resistors in series. I'm going to use this blue color. I've got those 3 resistors in series. So let's do those 3 resistors in series. So we have a series setup, and that means that R equivalent triple prime is R1 plus R equivalent double prime plus R2. So I'll redraw my circuit now. There we go. And now I can start figuring out the currents and the voltages, and then I work backwards, just like I did in the capacitor problem. So for a resistor, we know the voltage drop across a resistor is IR, the current times the resistance of that resistor. That means that the current through this equivalent resistor is going to be VAB over R equivalent $10 amps. So that's the total current. That's I total, right? And now we can step backwards. We know the potential difference across that resistor is just delta VAB. So we're going to sort of work our way now going backwards. So we're going to draw this other circuit. I'll redraw it here. R1, R equivalent double prime, and R3. And so we know the current here is 10 amps. So we know that delta V for R1, I guess I could just call it delta V1. Oops. Delta V1, that's the voltage difference across resistor number 1, is just I1 R1, which is 10 amps times its 4 ohms, 40 volts for R1. Delta V3 is going to be the same, I3 R3, and I is still 10 amps, and R is still 4 ohms, so we get 40 volts. And delta V for R equivalent double prime is I times R equivalent. And what do we get for that? We get 11. No. R equivalent double prime is 3. Now what we want to do is we want to do a quick check to make sure we got this right. We know that as we travel from point A around this circuit to point B, we have to go through a drop of 110 volts because delta VAB is 110 volts. So let's add them up. As we start at point A, we go across resistor R1, we drop by 40 volts. Then we go across resistor R equivalent, we drop by 30 volts. And then we go across resistor R3, we drop by another 40 volts, we add those up, and we get 110 volts. So that makes sense. That tells us we're on the right track. We didn't make a silly error somewhere along the way. Things look like they're working out here okay. So now we can take a step backwards and work our way up to the next part of the problem. So we're going to sort of jump back to this step. I'll redraw that down here. So we've got R1 R2, R3, and then we had some R equivalent over here. And let me just go back and refresh my memory. That was 12 ohms. So we know that the voltage drop from this point to this point, what am I going to call those? C and D. Let's see. Delta V, C, D, we know that's the same as the, I can label it over here if you'd like. This would be point C and this would be point D. So we know that that's 30 volts. And so delta V2 is I2 R2. And we know what delta V is. It's 30 volts. So that means that I2 is 30 volts over 4 ohms. .5 amps. And then we can do the same with the current through R equivalent is going to be delta V over R equivalent, 30 over 12 ohms, 2.5 amps. So we know the current through each of those two resistors. And let's take a quick stop here for a sanity check. If the current over here is 10 amps, then when we get to point C, that splits out. Part of it goes that direction, part of it goes that direction. Those two currents added together better be 10 amps, right? It doesn't have any choice. If it gets to that point, it splits. It doesn't disappear. So this we're saying is 2.5 amps in that direction, and this is 7.5 amps in this direction, and we add those up and we get 10 amps. So it makes sense so far. It looks like we haven't made any mistakes. Okay, and the last step we want to do is go back and add those three resistors at the end, convert R equivalent prime back into its three components so that we get back to our original circuit. That was R1, R2, R3. And we know that this current is 2.5 amps, and there's no place for it to go, right? Those three are in series, so the current is 2.5 amps everywhere in that branch of the circuit. So now we can find their delta V's across each one of those. Delta V4 is I4 R4, 2.5 amps times 4 ohms, 10 volts. And delta V5 is also the same, and delta V6 is the same. So I'm going to stop this video for just a second and put a summary table in and then restart it for you. So that's a summary of the results for the current and the potential difference across each resistor. And the idea here, start small. Look for something some couple of resistors in series, combine them and start working your way down. Hopefully you can get to the point where you only have one resistor, and then it's easy to figure out the current and the voltage, and then step backwards and see if you can split it out and find the current and the voltage in each step as you work your way backwards.